This past Sunday evening, a piece of the sun, several times wider than Earth, exploded. The light crossed 93 million miles in 8 minutes and reached us almost instantly. The moment it arrived, radios went dead across an entire side of the planet. Pilots over the Pacific lost contact, and operators across the Americas heard static. Forecasters logged it as a Class M 6.8, a strong solar flare. It was the most powerful shot the sun had fired in many days. And here is the part that should stop you cold. The sun was not even aiming at us when it happened. So this whole story turns on one simple but very hard question. Was that a warning we should heed, or only a rehearsal? If you value breakdowns like this, 1. Subscribe and stay with me. Drop a comment below telling me where you are watching from. Now let's stop circling that question and get straight into it. Part 1. The flash that killed the radios in 8 minutes. Let me rebuild what actually happened, not as news, but as a physical event. The sun is not a calm object sitting quietly in the sky. It is a ball of electrified gas with a violent, twisting magnetic field. That field is anchored deep inside the sun and dragged around constantly. In some regions, it winds itself tighter and tighter, like a stretched rubber band. Twist a rubber band far enough, and it snaps without any warning at all. When the sun's magnetic field snaps, it dumps enormous energy in just minutes. We call that sudden release a solar flare, and this weekend produced a strong one. The energy in a single large flare dwarfs anything our civilization can produce. We are talking about the output of many billions of power plants at once. The region responsible had only just rotated into view a few days earlier. Forecasters numbered it AR 4473 and flagged it as one to watch. NASA's Solar Dynamics Observatory, a spacecraft built to stare at the sun, caught it all. That spacecraft watches in wavelengths our eyes can never see directly. It measures the X-ray output that defines exactly how strong a flare is. Early Sunday, the region fired a smaller flare, a Class M 2.6. That one knocked out high-frequency radio over the Pacific and Eastern Asia. Forecasters logged it as an R1 event, the mildest radio blackout level. That was only the warm-up for what came roughly 12 hours later. Then, at 17 minutes past 7 in the evening, universal time, it let go. The big flare peaked on the summer solstice, the longest day of the year. Forecasters classed it M6.8, near the very top of the moderate band. Let me be precise, because these letters and numbers are not random labels at all. Flares are ranked B, then C, then M, then X, by their X-ray energy. Each letter means roughly 10 times the energy of the one before it, so a C flare is 10 times a B, and an M is 10 times a C. That makes an M6.8 strong, but it is not the largest class. An X flare would be another full step up in raw power. Hold that distinction, because it matters enormously later in this story. When the flare's light hit Earth, it slammed into the upper atmosphere instantly. It charged up the ionosphere, the electrically active shell high overhead. That shell is the mirror our long-range radio normally bounces off to travel far. A signal leaves the ground, hits that layer, and bends back down past the horizon. With the mirror suddenly overloaded, the radio waves were absorbed instead of reflected. The signal went up into the charged layer and simply died there. Forecasters logged an R2 radio blackout over the Americas and the Eastern Pacific. That sounds abstract until you ask who actually depends on those frequencies. Aircraft crossing the oceans use them when no other radio can reach. Ships at sea and emergency crews in remote country lean on them too. For a stretch on Sunday evening, that tool simply went dark for them. Now notice the timeline, because it is the first hard lesson in this whole story. 8 minutes passed between the flare and the dead radios over an ocean. 8 minutes is simply the travel time of light across that vast distance. That is not really a warning, because nothing on Earth moves faster than light. By the time you can measure the flare, its effects have already arrived here. There is no alert that can outrun a beam of light to the planet. Some of what the sun does to us cannot be dodged by anything we have. We can see it coming only in the sense that we see lightning. The flash and the strike are, for all purposes, the same instant. The flash, though, is not the part that frightens the engineers the most. It blacks out radio for an hour, and then the air recovers. The slower weapon is the truly dangerous one, and this week it nearly reached us. Let me put the energy of that flare into terms you can actually hold. A single strong flare releases the energy of many millions of large bombs. That energy leaves the sun as light, so it spreads out as it travels. By the time it reaches us, it is thinned across the whole daylit Earth. Even thinned that far, it was enough to silence radio over an entire ocean. The instruments that caught it measure the X-ray glow many times each second. They watch the brightness climb, peak, and fade across a few short minutes. That rise and fall is the fingerprint forecasters use to rank every flare, and this one ranked high, the strongest seen from the sun in many days. The blackout it caused was brief, lasting roughly an hour before it faded. An hour is survivable, even trivial, for almost everyone safe on the ground. But an hour without long-range radio is not trivial over the open ocean. A pilot mid-Pacific has no cell tower and no other link back home. For that stretch, the busiest air corridors lost a tool they assume is always there. To understand why it missed, we have to look at where the sun was aiming. Part 2. Why the sun's biggest shot this year missed us. A large flare usually launches something far heavier than light alone. It launches an actual piece of the sun's outer atmosphere into space. We call it a coronal mass ejection, and that name is far too polite. Picture 1 billion tons of electrified gas threaded with the sun's own magnetic field. Now picture it hurled off the surface at over 1 million miles an hour. The flash only dazzles your radios for an hour or so, and then passes. This cloud is a different kind of thing entirely from the light. If it lands squarely on Earth, it can pull current through a whole continent. The flash is the muzzle blast, and the cloud is the cannonball that follows it. This weekend's flare did launch one of these clouds out into space. Forecasters spotted the telltale signature almost immediately in their instruments. A flare that throws a cloud often gives off a particular radio sweep. That sweep is the sound of a shockwave ploughing through the sun's atmosphere. They named it and clocked it, moving near 380 kilometers per second. Later, special cameras called coronagraphs watch the cloud itself billow outward. They block the sun's bright disk so the faint cloud becomes visible against space. So the heavy ammunition was fired, and that much was certain within hours. The only question left was where exactly that cloud was pointed, and the answer is the reason you slept soundly through all of it. AR-4473 was not sitting in the center of the sun's face. It sat near the eastern edge, off to one side of the Sun-Earth line. A cloud thrown from that position tends to sail off to the side of Earth. Think of a punch thrown from the far corner of a crowded room. It was never aimed where you are standing, so it misses you completely. The geometry is unforgiving in both directions, and this time it helped us. Forecasters ran that geometry and reached exactly that reassuring conclusion. The main cloud from this flare would sweep east of Earth and miss us. The cannonball was fired, into the empty space beside the target. What we did receive this week was only the scraps left far behind. 2 weaker clouds, launched on the 19th and 20th of June, were already drifting our way. A stream of fast solar wind from a gap in the sun was also due to arrive. That gap is called a coronal hole, a place where the field opens outward. From those holes, solar wind escapes faster than the slow background flow. When that fast stream catches the slow wind ahead, it piles up and disturbs us. The combined forecast for the 23rd and 24th called for at most a G1 storm. That is minor, the lowest rung on a 5-step ladder of geomagnetic storms. The scale runs from G1 up to G5, the most extreme level. AG1 mostly nudges the aurora a little south and rattles grids slightly. It is the kind of thing forecasters log routinely and barely mention. And even that minor forecast has mostly underdelivered so far this week. Earth's magnetic field has stayed quiet to only slightly unsettled throughout. The clouds that did reach us came in weak and poorly aligned for trouble. The aurora stayed suppressed, and the grids never noticed a single thing. By every official measure, this has genuinely been a quiet week for space weather. A strong flare missed with its main weapon, and the leftovers barely registered at all. If you only read the official scale, nothing happened here worth a headline, and that is exactly the trap I want to pull you out of now. So you might fairly ask why this is worth your full attention at all. Here is the honest reason, stated as plainly as I can possibly put it. We watched a region capable of an R2 blackout fire, its biggest shot yet. We watched it launch a billion-ton cloud at over 1 million miles an hour. The only thing that spared us was the angle, not our defenses or our planning. Let me say that again, because it is the whole point of this part. It was not vigilance, not engineering, and not any kind of preparation at all. It was the angle, and nothing more than the angle, that saved us. And angles on the sun change every single day, without ever asking us. The region that fired this shot is already turning, slowly, towards us. It is worth pausing on how confidently forecasters can call a miss like this. The coronagraph images show the cloud expanding as a bright arc against black space. From the shape and direction of that arc, they judge where it is headed. A cloud from the center of the disk grows as a full halo toward us. A cloud from the edge leans clearly off to one side instead, like this one. This one leaned east, away from the line that connects us to the sun. So the relief this week was not a guess or a hopeful assumption at all. It was a measurement, read straight off the images within a few hours. That same measurement, run on a centered region, would have read very differently. The tools that reassured us this week can just as easily alarm us next time. They are honest instruments, and they will report a hit as plainly as a miss. That brings us to the patch of sky we should all be watching right now, Part 3, the region that is quietly turning to face us. The sun rotates, though not like a solid ball, because it is made of gas. Different latitudes spin at different speeds, which is strange to picture at first. The sunspot regions near its equator take about 27 days to come around. So a region on the eastern edge today is being carried steadily toward the center. It is turning, hour by hour, toward the line that points straight at Earth. Remember the punch thrown from the far corner of the room earlier. Now imagine the puncher slowly walking until he stands right in front of you. The fist itself has not changed at all, only the direction it now points. That is precisely what solar rotation does to a dangerous region over days. AR 4473 is on exactly that slow walk across the disk right now. And I want to be careful because the honest picture here is genuinely mixed. On one hand, The region weakened over the past day. In a hopeful way, it lost the most dangerous knot in its magnetic structure overnight. Forecasters call that knot a delta, and losing it is real good news. A delta is where opposite magnetic poles are crammed together inside one spot. That cramming is what stores the energy a big flare violently releases. Some of its smaller spots faded too, and a fading region is reassuring to see. A weaker region throws fewer and smaller punches as it slowly turns toward us. On the other hand, two facts complicate that comfort more than I would like. First, even a weakening region can fire a strong flare right up until it cannot. The energy already stored does not vanish the moment a spot starts to fade. Forecasters still describe this region as magnetically complex, the kind that produces real events. A complex region has its field tangled, and tangled fields snap without much notice. Second, and this is the thread to hold tightly, it is not alone up there. Behind it, rotating around the same eastern edge, sit at least two more complex regions. We did not have to wait for them to appear to know they were coming. Spacecraft and clever techniques let us watch the sun's far side in advance. They spotted these structures before they ever rotated into our direct view. Fresh regions, their full strength not yet measured, are turning toward us right now. So the central question sharpens into something concrete, answerable only with time. The question is not whether this weekend was dangerous, because it plainly was not. The question is the state of that whole side of the sun for 2 weeks. Picture 3 loaded regions, 1 fading and 2 unknown, all turning to face us. If they stay calm as they cross the center, this entire episode is a footnote. If one fires a strong Earth-directed cloud while facing us, we get the real test. That is the test we did not get this week, when the geometry quietly saved us. The geometry that saved us was luck, and luck is not a defense plan. The same rotation that spared us is steadily removing the very thing that spared us. Here is the uncomfortable logic the data forces onto the table right now. A moderate flare killed radio over an entire ocean while completely missing us. So picture, just for one honest moment, what a direct hit would actually do. Picture a stronger flare, an X-class flare, fired while the region faces us. Picture the billion-ton cloud, aimed not past us, but straight down our throat. The conditional is doing heavy work in that sentence, and I will not fake certainty. I cannot tell you that the next 2 weeks will bring such an event. Nobody can, and anyone who claims to is selling you false confidence. But to even weigh the danger, we must understand how the sun reaches the ground. We must follow the current from a magnetic snap to the wiring under your feet. Most people imagine a flare and a blackout as one simple thing, but they are not. There are 3 separate weapons, and only one truly reaches us. Let me explain how we can possibly know what sits on the sun's far side. Sound waves ring constantly through the body of the sun, like a struck bell. Those waves pass through sunspot regions and come back subtly changed by them. By reading the ripples on the near side, we infer the spots behind. It is a strange kind of sight, hearing the shape of what we cannot see. So, these 2 incoming regions were not a surprise when they rounded the edge. We had been tracking their shadows for days before they actually arrived. What we still cannot measure from behind is their exact magnetic tangle. That detail only resolves as they turn fully into our direct view here. And the magnetic tangle is precisely what decides how violently they can erupt. So we watch. 3 regions whose worst potential is only now becoming clear. 1 is fading, and 2 are question marks turning to face us. There is a reason forecasters do not relax just because a region is fading. Slow down here, because this next part is where the comfort breaks. The energy that drives a flare is stored in the twisted magnetic field. That stored energy does not drain away the instant a spot starts shrinking. A fading region can still snap and release what it has already built up. History is full of strong flares from regions that looked past their peak. So a shrinking spot is reassuring, but it is not a guarantee of safety. And this region is still rated complex, which keeps its ceiling uncomfortably high. The two regions behind it are the larger unknown in the whole equation. We can see their size, but not yet the magnetic tangle inside them. A large, simple region is far less dangerous than a small, twisted one. Until they face us fully, their true threat stays partly hidden from us. That mechanism is where we go next, and it is stranger than you think. Part 4. The 3 weapons, and only one reaches the ground. Most coverage of solar storms blurs 3 different things into one scary word. That blur is exactly where public understanding falls completely apart. So let me separate the 3 cleanly before we go any further. The sun sends us 3 distinct things during an event like this. 1. They travel at different speeds, and they do completely different kinds of damage. One arrives in minutes, one in hours, and one in days. One scrambles radio, one threatens satellites, and one can break the grid. Get them straight, and this entire threat finally starts to make real sense. Confuse them, and every news story about the sun will mislead you. The first weapon is the radiation, the pure light. Arriving in 8 minutes, it is X-rays and ultraviolet, moving at the speed of light itself. This is what caused this weekend's radio blackout high in the atmosphere. It charges that upper shell and scrambles the signals passing through it. It arrives with no warning, and it fades again within a few hours. It threatens aviation and navigation, but it does not, by itself, break the grid. Think of it as the dazzle of a camera flash in your eyes. It blinds you for a moment, and then your vision returns. Annoying and even dangerous in the wrong moment, but not structural damage. The grid on the ground barely feels this first weapon at all. The second weapon is the radiation storm, a flood of fast particles, mostly protons. These can arrive within tens of minutes to a few hours of the flare. They endanger astronauts, who may have to shelter in a shielded module aboard. A heavy dose of these particles is a genuine health risk in space. They also flip and corrupt the delicate electronics inside our satellites below. A single particle striking the wrong circuit can scramble a spacecraft's memory. A strong one forces airlines to reroute flights away from the exposed poles. Up high and near the poles, that radiation reaches aircraft far more easily. This weekend, thankfully, that particle threat stayed low across the board. The second weapon mostly stayed in its holster this time around. The third weapon is the coronal mass ejection, the billion-ton cloud from earlier. It is slow by these standards, taking a day or several to cross the gap, and it is the only one of the 3 that truly reaches the ground. Here is the mechanism, and I want you to feel it, not just file it away. When the magnetized cloud arrives, it slams the Earth's magnetic field and shakes it. Picture that field as a vast invisible web of limes wrapped around the planet. A strong cloud grabs that web and rattles it violently for hours on end. Now the simple physics that makes this dangerous, stated plainly. A moving magnetic field pushes electric current through any nearby conductor it touches. That is precisely how every electric generator on Earth actually works. Inside, spin a magnet near a wire and current flows in the wire. During a storm, the whole planet briefly becomes that spinning magnet itself. The shaking field drives current through anything long and conductive on the ground. And what lies on the ground, long and conductive, spanning entire continents. Power lines, pipelines, and the high voltage network carry electricity from source to distant city. During a big storm, those lines pick up current that was never meant to be there. The sky drives that current, not the power company. And it has a name. Engineers call it geomagnetically induced current, born from the storm above us. It is direct current, slow and steady, in a grid built for alternating current. That mismatch is exactly what makes it so destructive to the equipment. That current flows straight into the giant transformers at the joints of the grid. Here is the analogy that makes the whole thing finally click into place. Picture one of those huge transformers as a kettle built for a set amount of heat. The induced current is like a hidden burner switched on beneath that kettle. No one flipped it on, and no one can reach down to flip it off. The transformer saturates, overheats, and behaves in ways it was never designed for. Its core stops handling the magnetism cleanly and starts dumping heat instead. In a minor storm, that is just a wobble, the operators quietly correct. In a severe storm, the hidden burner runs hot enough to crack the kettle, and these kettles cannot be pulled off a shelf and swapped out quickly. The biggest transformers are custom built and can take a year or more to make. Only a handful of factories on the entire planet build the largest ones. They are so massive they must ship by specialized rail car across the country. Hold that single fact close, because it decides everything in the back half here. A cracked kettle in your kitchen is a trip to the store. A cracked transformer can be a year of darkness for a region. So 3 weapons leave the sun, and only the slow one reaches our wiring. But here is the twist that should unsettle you. Before we go on, even the gentlest storms, the ones we shrug off, have started erasing satellites. Part 5. The 38 satellites, a minor storm erased. I keep saying this week's storm was minor, and that minor storms rarely matter. I now have to complicate that claim, because of one quietly alarming event. There is a place where the word minor has stopped meaning safe at all. The story that proves it happened just a few years ago, in low orbit. It should change how you hear the word minor for the rest of this story, because the same kind of storm we shrugged off this week did real damage. Go back to the 3rd of February 2022, at a launch pad in Florida. SpaceX launched a batch of 49 Starlink internet satellites into space that day. Their practice was to drop them first into a very low parking orbit. That staging orbit sat only about 210 kilometers above the ground. There the satellites run checks before raising themselves to their working height. Low is cheap and tidy, since any failures fall and burn up fast. A dead satellite down there re-enters quickly and leaves no dangerous debris. But low also means skimming the thin top fringe of our atmosphere. Up there, even a small change in air density matters enormously to a satellite. And the air density at that height is not fixed, because it breathes with the sun. The day they launched, and the day after, a geomagnetic storm arrived overhead. It was a minor one, a G1, the very category we discussed earlier. The kind logged hundreds of times a cycle that almost never makes the news. But here is what a minor storm does that the headlines never mention. It pours energy into the upper atmosphere, and that energy heats it up. A heated gas expands, so the thin air swelled outward and upward fast. Suddenly, the air at 210 kilometers was far denser than the day before. The satellites were now plowing through thicker air than anyone had planned for. SpaceX measured drag on the new satellites running up to 50% higher. 50% more drag from a storm too small to make any headline. The satellites fought to save themselves against the thickening air around them. Operators commanded them to turn edge on, like a sheet of paper held into wind. That posture cuts drag to the bare minimum, so they tried to ride it out. It is the same trick as turning sideways to slip through a crowd. 11 of them managed to climb out and survive the storm safely. The other 38 could not escape the thickened air and lost altitude steadily. Within days, they spiraled down and burned up in the atmosphere below. 38 satellites gone, on a loss estimated near $50 to $100 million. It was the largest single event loss in that constellation's history to that date, and it came from a storm too minor to flag in the pre-launch briefing. Nobody warned them, because by the old rules, there was nothing to warn about. Sit with that for a moment, because it overturns the comfortable frame from earlier. I told you a G1 is something a grid operator glances at over coffee. That is true on the ground, where the official scale was built decades ago. The scale was calibrated for grids and radio, not for the density of air far overhead. Back then, almost nothing flew in that zone worth worrying about at all. The scale measures the wrong thing for the world we have now built. Now there are thousands of spacecraft in that drag-sensitive shell of sky. The large majority are part of these new mega-constellations of small satellites. The sky we depend on filled up faster than our warnings could adapt. Delores Nip, a space weather researcher at the University of Colorado Boulder, studied this loss. She has pointed out that this particular storm was not even a large one. She notes that in bigger events, the upper atmosphere can swell roughly tenfold. 10 times denser air hitting satellites a minor storm already dragged from orbit. Do that arithmetic, and the comfort drains right out of the room. Jonathan McDowell, an astrophysicist at the Harvard-Smithsonian Center for Astrophysics, drew a blunt lesson. He argued operators should simply deploy higher, where the thin air gives more margin. Around 300 kilometers, he suggested, at maybe 10% more launch cost. A small price, he implied, against losing dozens of satellites to a minor storm. So remember, the sheet of paper turned edge-on into the wind just now. Even that desperate trick saved only 11 of the 49 satellites. The same swelling of the air dragged spacecraft down in the big storm coming soon. It is one more clock ticking in only one direction, never the other. Every year, we put more satellites into that vulnerable shell of sky. The sun has not changed at all, but our exposure climbs without any pause. And here is the thread to carry forward into the next part. If a minor storm did this, our only real defense is warning. Stay with me, because that warning system has a brutal limit we rarely admit. Part 6. The half hour that is all the warning we get. There is one piece of good news buried in the slowness of the cloud. The flash arrives in 8 minutes, but the heavy cloud takes a day or more. That gap is the only opening our defenses have, and we have used it. We have parked spacecraft far up sun of the Earth, between us and the storm. They sit about 1.5 million kilometers away at a balance point in space. Scientists call that point L1, where the sun's pull and ours balance. A spacecraft can hover there for years, watching the wind blow past it. It is the closest thing we have to a buoy in the solar storm sea. When the cloud sweeps past those spacecraft, they take one last critical reading. They measure how fast it is moving and how strong its field is. Crucially, they measure which way that embedded magnetic field is pointing now. That last number, as you will see, decides almost everything about the damage. We get those readings somewhere between 30 and 60 minutes before impact. That half hour is the entire difference between Carrington's era and ours today. The telegraph men of 1859 had no idea anything was coming. They saw the aurora and the sparks at the very same moment. A modern grid operator gets a final warning and a chance to act on it. Half an hour of notice is not much, but it is everything we have. But I want to be honest about how thin that protection really is. 30 to 60 minutes is not long to safeguard a continent of equipment. It depends on people recognizing the threat and acting without any hesitation. They must act in the middle of what looks, at first, like an ordinary night. There is no klaxon in every control room when the buoy reads danger. There are humans reading screens and deciding whether to trust the numbers. And the warning only describes the storm we can actually see at L1. It cannot conjure spare transformers or rebuild a grid in half an hour. It buys reaction time, not invulnerability, and those are very different things. What can an operator even do with that half hour of notice? They can reduce the load on the most exposed lines and transformers. They can bring extra equipment online to share the coming strain. They can disconnect the most vulnerable pieces before the worst of it lands. These steps help, but they assume the storm behaves the way troubles the people who study this most. Our defenses were sized against the storms we have actually survived before. They were built for Quebec and tuned against the Halloween storms of 2003. We have never run the full test against a true Carrington-class event. We are prepared for the punches that have landed, not the one we fear. And the one we fear is precisely the one we have never taken. It is like a seawall built to the height of every past flood. It works perfectly, right up until the wave that clears the top. Hold that gap in your mind, because a near miss later will measure it exactly. So picture the chain we have built one more time before moving on. A flare's light is a slap that stings, disrupts, and quickly passes by. A direct cloud is a hand reaching down to pull current through our wiring. This week, the slap landed cleanly, but the hand missed us by the angle. Let me say that again, because it is the whole week in a single line. The slap landed and the hand missed, and almost no one noticed either way. Let me be concrete about what those defensive steps actually look like in practice. An operator warned of a severe storm can lighten the load on key lines. They can keep more generators spinning to share the coming electrical strain. They can postpone maintenance so the full network is available to absorb the blow. They can watch the most vulnerable transformers and pull them offline if needed. These are real and useful actions, and they have prevented real damage before. But every one of them assumes the warning is believed and acted on fast. A half hour vanishes quickly when a decision must cross several people and agencies. And the deepest problem is not speed, but scale and novelty together. The largest storm in our records is still smaller than the sun can throw. We are defending against the worst we have seen, not the worst that is possible. Picture a town that has flooded to 4 feet many times before this. It builds every wall to 5 feet and then feels perfectly safe. Then a flood arrives at 7 feet and the walls mean nothing at all. That is our exact situation with the sun, measured in current instead of water. Let me give the warning window an honest sense of proportion before moving on. 30 minutes is roughly the time it takes to drive across a small city. In that window, an operator must read the data and trust it completely. Then they must coordinate actions across a grid, serving millions of people. There is no app that hardens a continent at the push of a button. The steps are manual, deliberate, and spread across many separate control rooms. Some of those rooms may not even agree the threat is real yet, and the warning describes only the storm already measured at the L1 point. A second cloud behind the first can arrive with almost no notice at all. So the half hour is precious, but it is also thin and conditional. Technology brought us the warning, but only judgment turns that warning into safety. That near total silence is itself part of the danger, as you will soon see. Part 7. No, the sun is not breaking. We are. A question floods in every time a solar event reaches the news cycle. People ask whether the sun is acting strangely or escalating somehow lately. They ask if this is part of some larger, frightening, unprecedented pattern up there. They wonder if the sun is sick, or angry, or winding up to something. The honest answer, the one the data fully supports, is simply no. Not in the way people usually mean when they anxiously ask it. I want to answer it head on, because dodging it would be dishonest, and answering it honestly actually makes the real story scarier, not less. The sun runs on a cycle lasting roughly 11 years, swinging from quiet to active. At the quiet end, the disk can go days with almost no spots. At the active end, it bristles with complex regions, firing flares constantly. We are in the active phase of the cycle. Scientists call Solar Cycle 25. It reached its peak across 2024 and 2025 recently. It is still winding down from that peak even now, slowly and unevenly. During the active phase, this behavior is simply ordinary for our star. Complex sunspot regions form, fire flares, and launch clouds in every direction. Most of those clouds miss us, because Earth is a tiny target in a huge sky. The sun fires in every direction, and we occupy a sliver of one. What happened this weekend is not an anomaly at all by any measure. It is a normal day near solar maximum, and nothing more than that. There have been weeks far busier than this one in the last 2 years. So if the sun is not doing anything new, why does this deserve the hour? And that question right there is the real problem nobody quite names aloud. The sun has not changed across all of recorded human history. It behaved this way before there were humans to watch it at all. We have changed, and we have changed almost beyond recognition. That single fact is the whole reason any of this now matters. In 1859, the most advanced electrical technology was the telegraph. It was a few thousand miles of wire connecting a handful of distant cities. There was no power grid, no satellites, and no navigation beamed down from space. When the great storm hit, those wires sparked and threw current wildly. In some offices, the paper itself caught fire from the surging current. Operators sent messages with their batteries disconnected entirely from the line. The lines carried current straight from the storm raging in the sky above. It was a curiosity, a strange and beautiful night, and nothing more. Almost no human life depended on those wires, so life simply went on after. The sun threw its hardest punch, and the world barely had a jaw to hit. Now look at the device you are reading this on, at this very moment. Look at the grid, feeding it, and the satellites routing the signal to you. Look at the navigation in your pocket, and the timing hidden under the banks. Look at the pumps moving water and fuel through every modern city. Look at the data centers, the cell towers, the traffic lights, the hospitals. None of that existed in any real form a single human lifetime ago. We took the exact behavior the sun has had for billions of years. Then we wired our entire species into the one thing those storms attack. We built a nervous system for our civilization out of conductors and timing, and conductors and timing are precisely what a solar storm reaches out to touch. The threat did not grow at all over the centuries, but the target certainly did. We built that target, and we keep building it larger every single year. That reframing is the floor shifting silently under this whole story tonight. Keep it firmly in mind for absolutely everything that follows now. The sun is not the variable that changed here, because we are the variable. The danger is not that the sun got worse over time. It is that we ourselves grew more fragile while looking away. And to see that fragility clearly, we must visit the nights it already happened. The sun has hit a wired world before, more than once. Let me anchor this reframing with a single concrete comparison across time. In 1859, a person could lose nothing essential when the wires failed. They lit a candle and their day continued more or less unchanged after. Lose the grid today, and the candle does not bring back the water pump. It does not refill the gas station or restart the cold storage downtown either. The same storm meets a wildly different world on the receiving end now. We did not just add more wires, we made those wires load-bearing for survival itself. Food, water, money, heat, and communication now ride on the same fragile current. The sun fires the identical punch it always has across all the ages. We simply built a body that can no longer easily take the hit. That is the shift. And it happened almost entirely within living memory. The first of those nights lit up the sky over the entire planet at once. Part 8. The night the telegraph wires caught fire. Take yourself to the 1st of September, 1859, at a private observatory. A British astronomer named Richard Carrington was sketching a cluster of sunspots there. It was routine work, the patient daily record of a careful observer. Suddenly, he saw something no human had ever recorded before that morning. 2 brilliant points of white light flared up inside the sunspot group. They outshone the surrounding surface of the sun, then faded within minutes. Carrington had just watched a solar flare in ordinary visible light, directly. Another observer, named Hodgson, saw the same blinding flash that morning. The event was so powerful, it broke into the part of light we can see. Flares that bright remain extraordinarily rare even today, over a century later. He did not yet know what he had seen, only that it was new. What Carrington could not see was the cloud racing along behind that flash. It crossed the gap from the sun to Earth in about 17.5 hours. That is blisteringly fast for a cloud that usually takes several days. The reason it could is the same pattern running through history's worst storms. The sun appears to have fired more than one cloud in close sequence. The first one cleared the path, sweeping the ordinary solar wind aside. The second then came barreling through the cleared lane, almost unobstructed. It was a 1-2 punch, where the first blow only sets up the second. Remember that pattern, because you will see it again in a moment. The worst storms are rarely a single blow, because they tend to come in pairs. When the storm arrived, the sky lit up across the entire planet at once. Auroras, normally locked to the poles, appeared down in the Caribbean and Cuba. They appeared over Hawaii too, in places that essentially never see such lights. In the northeastern United States, the glow was bright enough to read a newspaper by. People woke and dressed for the day, convinced the dawn had come early. Gold miners up in the Rocky Mountains got up and started cooking breakfast. Compass needles swung and wandered as the magnetic field heaved beneath the storm. The whole planet's magnetism was being shoved around by the cloud above. And the telegraph network, the Victorian internet of its age, convulsed under the current. The lines surged with electricity, and operators received sharp electric shocks. Equipment sparked, and in several offices the paper records actually caught fire. Some lines failed completely while the storm raged in the sky above them. Others kept working with their batteries unplugged from the circuit entirely. They ran on nothing but the current the storm forced through the wire. In 1859, this was a wonder and a minor inconvenience. Nothing worse. A few burned offices and startled operators. And a strange, beautiful night. Hold that scene, because we are about to scale it up by a century. If that feels too far back to count as a fair warning, the sun repeated it. It gave us a second demonstration 62 years later, with far more wires waiting. In May of 1921, a great storm now called the Railway Storm swept Earth. Telegraph and railway signaling systems failed on both sides of the Atlantic at once. In New York, a railroad signal tower and control building caught fire that night. Parts of the telegraph network went down for hours across the region. That was a far larger world of wires than the one Carrington knew. The storm found every wire in it and forced its current through them all. 2 demonstrations, 62 years apart, delivered the same message in sparks and fire, and each time the world receiving the message was more wired than before. Hold that pattern, because the next demonstration came inside living memory. There is a detail from that night that still unsettles the scientists who study it. The magnetic instruments of the era did not just wobble during the storm. Many of them were driven clean off their scales, beyond what they could record. The needles slammed to their limits and stayed there for hours on end. We literally do not know the full size of the 1859 storm. Our best estimates come from ice cores and chemical traces left in the ground. Those traces suggest it was larger than anything measured in the entire space age. It was larger than Quebec and larger than the Great Storm of 2003. It was larger still by a wide margin than the May storm of 2024. So when I call Carrington the benchmark, understand exactly what that benchmark means. It is the largest event we can confirm, and it broke the instruments measuring it. The true ceiling of what the sun can do may sit higher still than that. It lasted only 90 seconds, and it put 6 million people into the dark. Part 9. 90 seconds that put 6 million in the dark. March 13th, 1989, began with a violently active sun overhead. In the days before, it had fired major flares and launched clouds toward Earth. They came in that same 1-2 pattern we just traced through history. One cloud cleared the road, and a second came charging down it. The clouds arrived in the early hours of the 13th and shook the field hard. The shaking was not gentle, but a deep and sustained heaving of the whole field. In the Canadian province of Quebec, that shaking drove current down into the ground, and Quebec, by an accident of geology, was the worst possible place for it. Quebec sits on a vast shelf of ancient, hard rock called the Canadian Shield. That rock is a stubbornly poor conductor of electricity beneath the surface. The induced current looked for an easier path and quickly found one nearby. It climbed into the long, high-voltage transmission lines of the Hydro-Quebec grid. Those lines stretch hundreds of kilometers from northern dams down toward the cities. They were exactly the long, conductive structures from our earlier mechanism. The current that could not flow through the rock flowed through the wires instead. Remember the kettle with the hidden burner switched on beneath it. Now that burner was running under an entire province's worth of transformers at once. The whole grid had quietly become the easiest path for the storm. What happened next happened terrifyingly fast for an entire power system. The induced current pushed the giant transformers into that overheating, saturated state. Distorted current began flowing through the carefully balanced network everywhere. The clean alternating current the grid expects was now riddled with the storm's signature. Voltage on the 735,000 volt system swung badly out of balance. It swung by as much as 15% in a matter of seconds. The grid's automatic protections read this as a catastrophic fault and reacted. They are built to disconnect equipment the instant something looks badly wrong. They began tripping offline, one after another, to save the machinery. As each one tripped, it dumped its load onto the others nearby. That pushed the survivors past their own limits almost instantly. The failure did not spread slowly. It avalanched across the entire network at once. The whole system came apart in less than 90 seconds flat that morning. From the first serious disturbance to a province-wide collapse, only 90 seconds passed. Let that figure sink in, because 90 seconds took the grid to total darkness. Roughly 9,450 megawatts of generation dropped off at once. 6 million people lost power in the dead of a Canadian winter night. It struck in the small hours so most simply woke to cold, dark homes. They had no idea a magnetic storm from the sun had done it. The blackout lasted about 9 hours for the majority of those customers. Some industrial sites waited considerably longer than that to come fully back online. Imagine a winter morning with no heat, no light, and no explanation. The same storm reached far beyond Quebec's borders on that single night. Far to the south, a large transformer at a New Jersey nuclear plant was damaged. That transformer took the strain quietly and paid for it later. Auroras appeared as far down as Texas, Florida, and Cuba once again. It was the height of the Cold War, and the blood-red sky frightened people badly. In more than one place, observers wondered if a nuclear strike had begun. There was even a space shuttle in orbit during the storm that week. It logged a strange sensor reading that cleared once the storm passed. The sun was reaching into orbit and into the grid on the very same night. Emmanuel Bernabeu, an engineer at the regional grid operator PJM, calls Quebec a wake-up call. He has said the blackout taught the industry to take induced currents seriously. He even believes the very same storm today would probably spare Quebec entirely. The grid was hardened after that night, and that work was real. That sounds reassuring, and the progress behind it is genuinely earned. But reassurance here only opens a larger and darker question immediately after. Because Quebec was a severe storm, yet it was not the worst the sun can do. Scientists estimate it was only about half as strong as the Carrington event itself. We hardened the grid against half of what the sun has already thrown at us. I want you to sit inside that frozen winter morning for just a moment. The furnace in most Quebec homes needs electricity to run its fan and controls, so the heat died with the lights. In a province built for deep cold, pipes began to chill in millions of homes within the first few hours. Hospitals switched to generators and watched their fuel gauges with new attention. Traffic signals went dark across cities, still half asleep in the pre-dawn quiet. None of this was caused by a war or a storm of wind and rain. It was caused by a magnetic ripple from a star 93 million miles away. The people shivering that morning had no way even to understand why it happened. That gap between cause and lived experience is part of what makes this threat so strange. Hold that comparison tight, because the storm that found new victims is next. Part 10. The storm that found the cities that thought they were safe. If you want to file Quebec away as a freak one-off, the sun objects strongly. It gave us another hard lesson just 14 years after that frozen night. In late October of 2003, a barrage of enormous flares hit Earth. These were not modest flares like this weekend's M6.8 at all. Some were X-class monsters, the very top of the scale and beyond. Wave after wave of clouds arrived in what we now call the Halloween storms. This time the grid that buckled was not in the frozen subarctic at all. It was in Malmö, a city in the south of Sweden, far from Quebec. The sun had simply moved its aim to a new and unsuspecting place. About 50,000 people there lost power for roughly an hour during the storm. That alone fits the pattern we already understand from the Quebec collapse before it. It was induced current, saturated transformers, tripped protections, and then the lights going out. But the Halloween storms did something that should genuinely unsettle you more. They reached down into South Africa, far from the vulnerable polar regions. Engineers there had long assumed their low latitude kept them safe from this. The textbooks said the danger lived near the poles, not near the equator. The storm did not read those textbooks, and it found the engineers. Anyway, the slow drip of induced current damaged a series of large transformers there. Some of those transformers degraded so badly they had to be fully replaced. And here is the cruelest detail. in the whole South African story. That damage revealed itself gradually over the following months, not at night. The lights did not go out in a dramatic 90-second collapse there. Instead, the transformers were quietly cooked and then failed weeks and months later. Remember the kettle that cracks only after the hidden burner runs long enough? South Africa was the kettle that cracked quietly, well after the storm passed. That delay is one of the cruelest features of this entire threat. The bill does not always arrive while you are still watching the sky. Sometimes the transformer simply ages a decade in a single bad night. Then it fails later, and almost no one connects the failure to the sun. The storm can wound the grid without anyone seeing the wound at all. The Halloween storms reached past the grid and into the sky as well. Satellites were knocked out or badly degraded across many different orbits. A Japanese Earth observation spacecraft was lost entirely during the event itself. Airlines rerouted their polar flights to avoid the heavy radiation overhead. Astronauts on the station took shelter from the elevated radiation around them. Each of these effects was survivable on its own, taken alone in isolation. But together, they show the sun probing every system we have come to depend on. Grid, satellites, aviation, and orbit. The storm reached into all of them at once. I want you to feel the weight of what this string of events means. Carrington burned the telegraph, the only network of its age, in 1859. Quebec collapsed a modern grid in 90 seconds back in 1989. The Halloween storms found Sweden, South Africa, satellites, and the polar air routes. Each storm reached further into a world that kept wiring itself together tighter. The sun did not learn to aim any better over those decades. We simply kept handing it more and more targets to find. Now hold the single most important comparison in this entire story once more. The storm that took down Quebec was undeniably a severe event by any measure. Yet scientists estimate it was only about half as strong as Carrington itself was. A storm half the size of Carrington still collapsed a grid in 90 seconds. It put 6 million people into a freezing winter blackout overnight. The full 1859 version is the one we have never faced in this era. We have only ever experienced the warm-up, never the main event itself. And the systems that warm-up threatened were far simpler than today's. Let me give you a sense of the raw scale of those Halloween flares now. The sun fired some of the most powerful flares ever recorded that fortnight. One was so intense, it overwhelmed the very sensors built to measure it. The instruments saturated, much like the needles back in 1859 had done. So even our modern measurements of that storm carry a question mark at the top. And the storm kept coming in waves, day after day, for nearly 2 weeks straight. Each wave found a new system to test and a new weakness to expose. There was the grid in Sweden and the transformers far away in South Africa. There were satellites failing or degrading in nearly every orbit around the planet. A spacecraft heading toward Mars even took damage far from Earth entirely. The sun was not aiming at any one of those targets specifically at all. It simply flooded the whole neighborhood, and our machines were standing in it. There is something genuinely insidious about that delayed kind of damage too. A transformer cooked by a storm may keep running for weeks afterward. It looks fine on every gauge, while its insulation quietly breaks down inside. Then one ordinary day, with no storm in sight, it simply fails outright. The utility blames age or bad luck, and never once suspects the sun. So the true toll of a storm can be scattered across months of failures. That scattering hides the real size of the threat from the watching public. We tend to count only the damage we can see on the night itself. The slow damage never makes the headline because it has no dramatic moment. It is the difference between a wound that bleeds and one that festers unseen. The festering kind is harder to treat because no one names the cause. The most dependent systems of all are the ones you cannot even see. Part 11. The invisible clock the whole world runs on. There is one more layer here, and it is the hardest one to believe. So let me build it carefully, piece by piece, before you dismiss it. Lean in for this one, because almost no one sees it coming. When you imagine a solar storm hurting you, you picture the lights failing. The grid is the obvious target, and we have covered it thoroughly already. But the grid is not the only thing the sun can reach and touch. Some of the other targets are wired so deep that we forget they exist. We use them every hour and never once think about where they live. And almost all of them trace back to a single, fragile thing. Start with a navigation system sitting in your pocket right this minute. You think of it as a tool for finding a nearby restaurant quickly. But those satellites are not really broadcasting maps down to you at all. Each one carries an atomic clock and broadcasts the exact time, endlessly. Your phone listens to several at once and compares when each signal arrives. From those tiny timing differences, it works out exactly where you stand. That whole trick is timing measured down to billionths of a second. So the system is really a fleet of flying clocks, not a map. And once a free, perfect clock hangs in the sky, we use it everywhere. We could not resist building on something so precise and so free. The timestamps that let banks agree on transaction order lean on that clock. The synchronization that stops cell networks from talking over themselves uses it. Parts of the power grid itself use it to keep their current in step. Data centers, surveyors, shipping fleets, and self-driving farm gear all drink from it. We threaded one invisible dependency through nearly everything, then forgot we did it. It works so silently and so reliably that we stopped noticing it at all. We built floor after floor on top of a foundation we never inspect. And a solar storm is one of the few things that shakes that foundation. Now here is what a solar event does to that hidden clock above us. The flare's radiation charges the ionosphere, the same shell that blacked out the radio. Navigation signals must pass through that shell to reach the ground below. When the shell is disturbed, the signals arrive slightly early or slightly late. The perfect clock goes fuzzy, and the precision quietly falls apart for a while. In the storm of May 2024, that is exactly what hit farmers. It struck in the middle of the American planting season, the worst possible week. Self-driving tractors guided by satellite began wandering off their crop rows. Some shut down entirely in the middle of the field, mid-task. Farms parked their expensive equipment and waited the sun out for days on end. Picture that clearly for a moment, because it sounds almost absurd to say aloud. A storm on the sun reached across 93 million miles to stop a tractor. It stopped that tractor in a field in Nebraska several days later. The chain runs from a magnetic snap on a star to a stalled planter. It sounds impossible, and yet it simply happened, and it will happen again. This is why I keep insisting the target is the thing that grew. None of this timing web existed in any real form for Carrington in 1859. Most of it did not exist for Quebec in 1989 either, really. We spent the last few decades threading precise time from space into everything. Then we mostly forgot that we had quietly done it at all. Stay with me, because one last coin flip decides our fate entirely. Let me make the banking dependency concrete, because it sounds abstract until you see it. Modern markets execute trades in millionths of a second all over the world. For those trades to agree on order, every computer must share one clock. The cheapest perfect clock available is the timing signal beamed down from space. So a great deal of global finance is quietly synced to those satellites. Telecom networks do the same to hand your call from one tower to the next. Even some power grids use that space timing to keep their phases aligned. Pull the clock away, and these systems do not stop instantly or dramatically. They drift, and they throw errors, and they lose their shared sense of now. The failure is quiet and strange, which makes it much harder to diagnose fast. We built a single point of dependence and scattered it through everything at once, and almost no one who relies on it could even tell you that they do. Consider just how many of those satellites now hang above us all at once. There are thousands of active spacecraft circling the planet at this very moment. A large share of them sit in the low, drag-sensitive shell we discussed. Every one of them depends on an atmosphere that the sun can inflate. And on the ground, billions of devices quietly trust the timing from above. Your bank, your phone, and your power company are all in that web. None of them advertise the dependence, and few of their users ever suspect it. We have woven the convenience so tightly that we can no longer see it. That is the strange shape of this particular vulnerability we have built. It is everywhere and invisible at the very same time, which is the trouble. A threat you cannot see is a threat you will never prepare for. It happens at a door we built, but absolutely cannot. The coin flip at the door we never control. Let me close a loop. I deliberately left open several parts ago now. I told you the clouds this week arrived poorly aligned for any trouble. Here is exactly what that alignment means and why it spared us completely. It is the single most important coin flip in all of space weather. Get this one idea, and you understand why some storms wreck us. You also understand why others, just as large, pass almost unnoticed. Think of the Earth's magnetic field as a door held shut against the wind. The incoming cloud carries its own magnetic field along with it, through space. The direction that cloud's field points decides whether the door holds firm. If the cloud's field points the same way as Earth's, roughly northward, they press together. The door stays shut, and most of the storm's energy deflects around the planet. The cloud slides past, and the lights stay on, and you sleep through it. If the cloud's field points the opposite way, southward, the two fields link up fast. The door swings wide open, and the storm's energy pours straight inside us. The same cloud can be harmless or catastrophic, depending only on that direction. Same cloud, same speed, same mass, same everything else about it entirely. The only difference is which way that embedded field happens to be pointing. And that direction was set back at the sun days before it ever arrived. We cannot control it, and we can barely predict it until L1 reads it. This week, the door stayed shut, and that is the second half of our luck. The clouds that reached us arrived oriented in a way our shield turned aside. That is a large reason even the glancing blows did almost nothing here. Flip that orientation with the very same clouds, and this becomes a different week. So when I say we got lucky, I mean it in two stacked ways at once. We got lucky on the geometry because the big cloud was aimed sideways. And we got lucky on the orientation because the leftovers knocked on a closed door. Two coin flips, both landing in our favor, and we arranged neither of them. Hold that, because it is the honest foundation under everything that follows here. Our safety this week was not earned by vigilance or by clever engineering. It was handed to us by an angle and a direction we cannot set. The same two coins decided the fate of every storm in this story. Carrington's coins came up southward and aimed, and the wires burned that night. Quebec's coins came up southward and aimed, and a whole province went dark. The Halloween coins came up the wrong way too, and 3 continents felt it. Now think about what that means as those new regions turn toward us. Each future cloud carries its own pair of coins flipped back at the sun. We will not know how they landed until 30 minutes before impact arrives. The warning at L1 is in part simply us reading those coins late. It tells us how they fell, far too late to change anything at all. It only tells us how hard to brace before the blow finally lands. And bracing, as we already saw, has very real limits of its own. Keep both coins in view, because a near miss once showed us the worst flip. The sun has already fired a perfect catastrophic shot in our direction. Let me be honest about why we cannot simply predict that direction in advance. The cloud's magnetic field is twisted and folded as it leaves the sun. It can rotate and reorder itself across the long days of its journey here. Two clouds can even merge on the way and scramble each other completely. So the orientation that finally arrives is not reliably set when it first launches. We can guess at it from the launch, but the guess is genuinely weak. The only firm reading comes when the cloud reaches the spacecraft at L1. At that point, it is roughly 30 to 60 minutes from striking us directly. So the single most important fact about a storm arrives almost last of all. We learn whether the door will hold only as the cloud reaches the handle. That is not a flaw we can engineer away with better instruments anytime soon. It is built into the physics and the vast distances involved here. Every region now turning toward us carries its own unread coin. This is the part that humbles even the people who do this for a living. We can predict where a cloud is going with fair confidence now. We can predict roughly when it will arrive within a few hours of truth. But the one number that matters most stays hidden until the very end. The orientation of that field is set by chaos deep inside the sun. It is shaped by the violent, tangled way the cloud was first born. No model on Earth can yet read it reliably days ahead of arrival. So, we forecast the weather while blind to its most important single variable. Imagine a hurricane forecast that could not tell you the wind direction at all. You would know the storm was coming, but not whether it would flatten you. That is roughly where we stand with the largest solar storms even today. The only reason you have never heard about it is timing. Part 13. The Carrington-class hit that crossed an empty orbit. I told you we have never faced a full Carrington-class storm in the electrical age. That is true, but we came within a hair of facing exactly one. Almost no one noticed because timing and geometry saved us once again, silently. This is the near miss I promised you, and it is the scariest part. In July of 2012, the sun launched a cloud of extraordinary power outward. A spacecraft that happened to be watching measured it carefully as it passed. That spacecraft sits off to the side of Earth's orbit, watching the sun. By its analysis, this was a true Carrington-class event in every respect. It was in the same league as the legendary storm of 1859 itself. The sun had fired its hardest punch, the kind we most fear. It came screaming across the inner solar system at tremendous speed that month. It crossed the orbit of the Earth, right through our path around the sun. So the cannonball flew straight through the racetrack we run on. The only reason you have never heard the date is one of pure timing. Earth was not standing at that point in its orbit when it arrived there. We had passed through that exact spot about 9 days earlier already. We moved on along our orbit, and the cloud crossed empty space instead. It sailed through the place we had recently been and vanished off into the dark. Just 9 days was the entire gap between a quiet footnote and a global catastrophe. If the sun had fired a week and a half later, we would know that date. Daniel Baker, a space scientist at the University of Colorado, led the analysis afterward. He and his colleagues reconstructed exactly what that cloud would have done to us. He has said plainly that a direct hit would have left us recovering for years. We would still be picking up the pieces in his blunt assessment of it. Let me give you the number that explains what picking up the pieces means. The United States National Academy of Sciences studied a Carrington-scale hit on modern infrastructure. They tried to put a price tag on the worst plausible storm. Their estimate for the cost, in the first year alone, reached nearly $2 trillion. That is not 2 billion, but 2 trillion with a T in the first year. They estimated 20 to 40 million people could face an extended power outage. And the outage in the worst hit areas would not last mere hours. It would not last only days either, in their sobering assessment of it. It could run anywhere from 16 days to 1 or 2 full years. Read that number again, because it is not days, but up to 2 full years. Now connect that back to the detail I planted way back in part 4. Why would any blackout possibly last a full year in a modern country? Because of the transformers, the custom kettles that crack under the hidden burner. Remember, only a handful of factories on Earth even build the largest ones. Brace for this next fact, because it explains a year-long blackout. A single unit can take a year or more to manufacture from scratch. They are so large, they must ship by specialized rail car across the country. The grid is built to lose a transformer here and there and replace it. It is not built to lose dozens or hundreds in the same 90 seconds. There is no warehouse of spare giant transformers waiting for that catastrophic day. So the lights would not come back when the storm ended. They would come back when the factory's finished, one slow unit at a time. Let me dwell on the transformer problem, because it is the hinge of the whole disaster. The largest grid transformers are not standard parts you can stockpile cheaply. Each is tuned to the specific grid and the specific voltages it must serve. They weigh hundreds of tons and stand roughly as tall as a house. The factories that build them are few, and most sit outside the country needing them. An order placed today can take well over a year to actually fill. In normal times, that is fine, because failures come one at a time. A utility loses a transformer, orders a replacement, and limps along in the meantime. But a severe storm does not damage them politely, one at a time. It can stress every large transformer on a continent in the very same hour. If even a fraction of them fail, the replacement queue stretches well past a year. There is simply no surge capacity in the world to build hundreds quickly. That single bottleneck is what turns a one-day storm into a one-year blackout. The sky clears in a single day, but the supply chain does not. And do not imagine this is only a problem for one country alone either. The grid is interconnected across borders, in ways most people never picture. A failure that starts in one nation can spill into its neighbors quickly. The transformer factories that serve the world sit in just a few places. So a global storm would put every affected country in the same long queue. There would be no spare nation to lend a continent its giant transformers. Everyone would be rebuilding at once, drawing from the same thin supply. That is what makes a severe solar storm a truly planetary kind of risk. It is one of the few hazards that can strike the whole world together. Most disasters are local, and the unaffected rush in to help the affected. A great solar storm would offer no such outside rescue to lean on. That is the real danger, and it arrives after the sky goes quiet again. Part 14. The year in the dark no one has a plan for. I want to make that span, 16 days to 2 years, feel concrete now. The number is far too easy to read past without truly flinching at it. So think about what runs on electricity that you never picture that way. Start with the water that comes out of your tap each morning. That water is pushed to you by electric pumps somewhere down the line. The fuel at a gas station is lifted from underground tanks by electric pumps too. So, in a long grid failure, the gas stations themselves stop working entirely, and then the trucks that resupply everything else have nowhere to refuel. The whole web of delivery seizes up once the pumps go quiet. Refrigeration stops in your home and in every store and warehouse around you. The cold chain that holds a city's food and its medicine simply fails. Insulin spoils, vaccines spoil, and the frozen reserves of a whole city thaw quietly. Cell towers run on batteries that last only a matter of hours at most. Then backup generators carry them, but only as long as their fuel lasts. After that, the towers fall silent, and your phone becomes a flashlight only. The thing you would use to call for help stops being a phone. Hospitals keep generators, but generators must be refueled to keep on running. And the trucks that refuel them need working pumps and clear open roads. None of this is exotic speculation about some far future technology at all. It is just the ordinary plumbing of a modern city suddenly exposed for what it is. All of it quietly assumes the grid will simply be there again tomorrow. Every system leans on that assumption, and the assumption almost always holds. For a few hours, the way Quebec lived it, that is a hard emergency. People shiver, wait, and the power returns before things truly unravel. For a few days, it is a serious crisis that outside aid can still reach. Neighboring regions send crews and supplies, and the system slowly recovers. But the National Academy scenario describes the worst regions waiting months on end. They might wait more than a year, while factories build one transformer at a time, and there is no neighbor to call when the whole continent is dark. A blackout measured in hours is just weather we endure and then forget. A blackout measured in seasons is something we have no real experience of at all. Let me say that the other way around, so it truly lands now. The thing that hurts you is not the flash in the sky above. It is not even the dramatic collapse of the grid in 90 seconds. It is how long the power stays off after the sky goes calm again. The eruption is over in minutes, and the aurora fades by the dawn. The danger is measured in the weeks and months that come after. The consequence can outlast the recovery from a major war between nations. That is the part the beautiful light show never shows you at all. And here is the cruelest twist hidden inside this whole arrangement we built. The more reliable the grid becomes, the less we plan for its loss. We have wired our lives around the assumption of constant, uninterrupted power forever. That assumption holds for years, then decades, lulling us into deep complacency. The rarer the disaster, the less ready the society becomes to face it. So the very reliability that serves us daily is what leaves us most exposed. The danger here is not only solar, it is human and psychological, and it lives in us. Keep that human blind spot in mind as we turn at last to the forecast. Let me give that complacency a concrete shape you can actually picture clearly. The last continent-scale grid disaster from the sun was Quebec in 1989. That is more than 3 decades of mostly quiet skies since the worst real hit. An entire generation has grown up simply assuming the lights always stay on. Budgets reflect that assumption because money flows toward the threats that people feel. A storm that comes once a century struggles to compete for attention or funding. Engineers who understand the risk often work against that current of public indifference. They harden a transformer here and add a monitor there, quietly and underfunded. Their work is real, and it has genuinely reduced the danger over time. But it races against a target that grows faster than any budget can keep up. The grid expands, the satellites multiply, and the timing web spreads wider each year. So, even as we get smarter, the dangerous gap can still widen beneath us. There is a quiet irony in how we tend to treat this particular risk. We insure our homes against fires that almost never actually come. We drill our children for emergencies that may never once arrive. Yet a storm that could darken a continent gets almost no public attention. The reason is simple and very human in its underlying nature. We prepare for the dangers that we can vividly imagine and remember. A solar storm has no smell, no sound, and no warning we can feel. Its last great blow landed before most people alive today were even born, so it sits in a blind spot, real on paper, but unreal in the gut. The engineers who fund the hardening fight that blind spot every budget cycle. They ask society to spend now against a threat it cannot quite picture. Two separate clocks are running toward each other at this very moment. Part 15. Two clocks running toward the same hour. Let me bring the two timelines of this story together at last now. This is where the dread stops being historical and becomes a live forecast. There are two clocks running, and they are running toward each other. The first clock is the sun's, and it runs on that 11-year cycle. Right now, it sits in the back half of an active maximum phase. Regions like AR4473 keep forming and rotating across the disk. That region and the complex ones behind it are turning toward us right now. Watch both clocks now, because their timing is the whole danger. This clock ticks in days for any single region facing the Earth. It ticks in years for the broader solar cycle as a whole. It is not asking our permission, and it never will at any point. The sun will keep firing in every direction, including, eventually, ours. The second clock is ours, and it runs in one direction only, forward. Every year, we add more transformers, more transmission, and more interconnection between regions. More links mean a failure in one place can cascade into another fast. We add more satellites to that drag-sensitive shell of sky every single year. We deepen our dependence on precise timing for things far from space. Our clock is a steady, relentless climb in exposure to this exact threat. We grow more vulnerable in absolute terms, even as our engineering improves. The engineering gets better, but the target gets bigger faster than that. So the gap between what could hit us and what we can absorb keeps widening. We got a clear preview of the modern version just over a year ago. In May of 2024, Earth took the strongest storm in 2 decades. It was a G5, the very top of the entire scale of storms. It was the first of that magnitude since the Halloween storms of 2003. The auroras were spectacular, seen at low latitudes around the whole world. For most people, that beautiful night was the entire story of the storm. They photographed the sky and went to bed, and nothing seemed broken. But underneath the light show, the systems were straining hard all night. The tractors wandered, as we saw, mid-planting across the American Midwest. Satellite operators watched their spacecraft sink as the heated air swelled around them. It was the very same drag mechanism that doomed those 38 Starlinks. The grids logged irregularities, and the system held, but it groaned audibly. We passed the test, but only barely, and only because it was brief. So where does that leave us this specific week, right here and now? Let me give you the honest forecast, with all of its uncertainty intact. Faking certainty here would be its own kind of quiet lie to you. There are 2 branches ahead, and the data leans toward the gentler one. In the first branch, AR4473 keeps weakening as it faces us. The complex regions behind it stay relatively quiet as they finally arrive. The next 2 weeks pass with only minor flares and small ripples. Aurora chasers get a few good nights, and the grid never notices anything. This whole episode becomes a reminder rather than any kind of disaster. The data, as of right now, genuinely leans this way, and I will say so plainly. The most likely version of the next 2 weeks is a quiet one. But the second branch is the one we cannot rule out just yet. One of these regions, while facing us squarely, fires a strong, fast cloud. That cloud arrives with its magnetic field pointed the wrong way for us. The door swings open, and we finally get the test we skipped this week. Nothing in the current data demands that this happens in the next 2 weeks, but nothing in the current data rules it out either, in all honesty. And these regions are exactly the type that has produced such events before. So we sit between 2 branches, watching 3 loaded regions turn to face us. 2 clocks are running, and neither one of them ever stops for us. Let me be clear about what I am and am not telling you tonight. I am not telling you a great storm is coming in 2 weeks. The honest, boring, most likely outcome is that nothing much happens at all. The sun quiets, the regions cross harmlessly, and the aurora gives a few shows. That is where the smart money sits as I lay all of this out. But I am also not telling you the threat is safely behind us now. The same physics that spared us this week guarantees nothing about the next one. The regions turning toward us are loaded, and the cycle is still active. Somewhere in the years ahead, the coins will come up the wrong way. When that happens, the only question that matters is whether we are ready. And readiness is not built in the half hour before the cloud arrives. It is built now in the long quiet, while nothing yet seems wrong. We do not get to set the hour that they finally meet. We only get to decide whether we are still watching when they do. Part 16. What we are not watching while we look away. The flare that opened this story is already over and completely gone now. Its light reached us, killed some radio for an hour, and passed on. The cloud it launched is already sailing east of us into empty space. By the time most people heard a word, the event was already history. That is exactly the pattern that makes this threat so easy to ignore. The dramatic part, the flash, and the aurora is brief and usually harmless. The dangerous part is rare, slow to build, and invisible until it lands. So our attention drains away in the long quiet stretches between events. And those quiet stretches are almost all of the time, by far, always. The systems that would protect us depend on people staying alert anyway. They depend on human vigilance through long years of nothing happening at all. They wait for a night that may never come on any one person's watch. Remember the half hour of warning we get from the spacecraft at L1. That warning is worthless if no one watches the screen when it counts. Remember the 2 coins, the angle and the orientation, flipped at the sun. We cannot control either one, and we read them both far too late. And remember, the year in the dark, waiting on transformers built one at a time. All of our protection comes down to attention paid during the quiet. Think about how this week will be remembered, which is to say, not at all. There will be no anniversary for the flare that missed us by an angle. No one marks the storms that did not happen to a wired world. The near misses leave no craters, no blackouts, and no headlines behind them. They leave only a forecaster's quiet note and a sky that stayed calm. And that is precisely why the next one can catch us completely unprepared. We do not learn much from the blows that land just beside us. We file them as nothing and let our attention drift back to the noise. The sun, meanwhile, keeps its own schedule, indifferent to our short memory. It will fire again and again in every direction across the coming years. Most of those shots will sail past us into the dark, unfelt. One of them, someday, will not, and we cannot know which one. So here is the line I will leave you holding tonight. Finally, the most dangerous moment is not the moment the sun finally erupts at us. It is the moment we collectively stop watching the sun at all. This week, the sun fired its biggest shot of the season toward us. It missed us by a matter of angle, and the world barely looked up. The region that fired it is turning to face us right now, tonight. Maybe it weakens, and this is truly nothing, as the data suggests it might. Probably it weakens, and this is nothing, and we all move on quickly. But it showed us something in 8 minutes and 1 dead band of radio. And the strange thing is how ordinary this whole week felt from the ground. There was no siren, no evacuation, and no breaking bulletin on the news. Most people slept straight through the largest solar shot of the entire season. The radios faded over the ocean and then quietly came back to life. The forecasters logged it, watched the clouds sail east, and simply moved on. By morning, the event was already a footnote in a quiet daily report. That ordinariness is exactly what should give you a moment of pause now. The biggest danger we face rarely announces itself as a danger at all. It showed us what our star can do when it is not even aiming. Picture again that piece of the sun, several times wider than Earth, that opened this story. Picture it turning slowly toward us across the next handful of days. Picture the door we cannot lock and the coins we cannot ever wait. We just watched the warming shot cross 93 million miles to reach us here. And I am left with the same hard question I started with tonight. The data refuses to close it, and I will not close it for you. We saw the shot cross the dark, and we felt its flash arrive. We simply do not yet know what that shot truly was. A warning we will finally heed, or only a rehearsal for the real thing.